we've talked about closures and interiors in a sort of very abstract sense involving all open sets, all closed sets. So I thought now I would give you the proposition that characterizes the closure and interior and boundary of a set in terms of balls of radius r, and perhaps you will find this a little bit more intuitive. So we start with a metric space. A subset of the metric space, this is a thing we're taking the closure and interior and the boundary of, and a point in our metric space. And then I'm going to state both these conditions and their contrapositives. So we'll say that X is in the interior of A if there exists a radius r greater than 0 such that the open ball centered at X of radius r is contained in A. And the converse is that X is not in the interior of A if then the contrapositive is that for all r greater than 0, the ball centered at X of radius r is not a subset of A, so it contains a point y that's not in the ball. That is, if you delete every point in A, you don't get the empty set. And then the closure, on the other hand, X is in the closure of A if for all positive radii, the ball centered at X of radius r intersect A. That is not allowed to be the empty set. It has at least one point in it. That is, X is not in the closure of A if there exists a positive number r such that the ball centered at X of radius r doesn't contain any points of A. And then X is in the boundary of A if for all positive radii r we have that the ball centered at X of radius r, it has to contain a point of A. The ball intersect A can't be the empty set, but it also has to contain a point that's not in A. And so the contrapositive is X is not in the boundary if there exists a radius r greater than 0 such that either of them is empty. Or, so if there's a ball that doesn't have any points of A, it's not in the boundary. And if there's a ball that it's contained in A, doesn't have any points not in A, it's on the boundary. So let's draw a picture of this. We'll use our half moon shape. And then a point, so this point inside the domain, you can draw a ball of radius r around it. You could think of this as building a wall around our center point of radius r, and it keeps out everything that's not in A. So the interior is all the points where you can draw a little wall around them. They can have some breathing room where they're not in A. And then the exterior, everything that's outside the closure, that would be the points where you can draw a little ball that keeps out everything that is in A. That would be the interior of the complement. That means everything but the closure. And then the points in the closure, well, maybe they're points in A. Well, if you start with a point in A, then obviously any ball you put around it is going to have a point in A, namely the middle point. But you also get points like this one, where any ball you put around it, no matter how small, it's going to pick up something in A. And so this is part of the closure. And then the boundary would be, remember, the boundary is the closure minus the interior. It's a point like this one where you can where any ball you draw around it, you're picking up some points that are in A and some points that are not. That works both for point in set. Boundary points can be in the set or not, but you can always draw a little ball around them. Any little ball you draw around them has a point in A and a point not in A. Remember, the boundary is always contained in the closure. So, and so is the interior. So we can, so all of my example closure points that weren't in the interior were in the boundary. And since the boundary is defined as the closure minus the interior, that's not too surprising. Okay, so let's prove this. Proof is actually not going to be too terrible. We're going to use some stuff we've seen before. Let's let X be in the interior of A. So this is an if and only if statement. So we will have to prove both directions. Then X is in G for some open subset of G, because that's the definition of interior. Interior is just the union of all the open subsets. So it's not quite the definition of open set. The definition of open set is that it's the complement of the closed set, but it's proposition 5.3.3 that says any point in an open set you can draw a ball around it. We just use that fact. So if X is in the interior, then this condition in terms of balls is true. I suppose I wasn't clear enough. These are all if and only if statements. Since I don't have to space to write if and only if, I'm going to just go through and turn them all into IFFs, if and only ifs. That, of course, means that to finish with part A, I have to prove the converse of this. So conversely, if X is a point in our metric space and there is a positive number R with ball centered at X of radius R contained in A, then we saw that open balls are in fact open, so the ball centered at X of radius R is an open set. So that means that G is a subset of A is a superset of G, but G is the ball centered at X of radius R, so that of course includes the point X. So that proves our if and only if statement at the start. If X is in the interior of A, then there's a ball centered at X contained in A. If there's a ball centered at X contained in A, then X is in the interior. And then, of course, the contrapositive, I will not bother to write out the proof. It's just the negation of X in the interior of A and the negation of there exists a positive radius such that the ball is contained in A. All right, now for part B, we're going to notice that the closure of A is, that's the complement of the interior of the complement. That's proposition 5.3.9c. So X is in the closure of A if and only if X is not in the interior of the complement. So we remember that means for all radius R greater than 0, the ball centered at X of radius R minus X minus A, that is not allowed to equal the empty set. But we'll notice that if you take the ball and you delete everything that's not in A, that's the same thing as taking the ball and keeping everything that is in A. So we see that X is in the closure if and only if this first condition, this for all R greater than 0 condition, is true. You can also show that X is not in the closure if and only if there exists a radius that's contained in the complement, that is, where the ball intersect A is empty. You can show that the same way. And then, since we recall, I said that the boundary of A is the closure of A minus the interior of A. So X is in the boundary of A if and only if it needs to have two things true. It needs to be in the closure of A, which we just saw means that for all radius R greater than 0, ball centered at X of radius R intersect A is not allowed to be empty. Every ball around X contains a point in A, and X is not in the interior of A, meaning that for all positive radii, the ball centered at X of radius R minus A, this ball has at least 1 point not in A. And that's exactly what was stated up to writing out the contrapositive, which I trust all of you to do. So that completes that proof. I want to give you an example of some sort of strange behavior that balls and their closure can get up to. So let's let xd be a metric space. X is a point in our metric space, R is a positive radius. And we've seen that the open ball centered at X of radius R, that's open, and it's obviously a subset of the closed ball. This is all the points whose distance to X is less than R. That's clearly a subset of the points whose distance to X is less than or equal to R. So if it's an open subset, it's got to be contained in the interior. And similarly, the closed ball, we saw it as closed, is a closed superset of the open ball. So that means that the closure of the open ball is contained in the closed ball. And in Euclidean space, that they are in fact equal to each other. So if you draw the open ball, and then the closed ball is just you throw in everything a distance r, then every single point that you added to the closed ball, well, it's got to be a boundary point of the open ball. It contains points in the open ball and points not in the open ball. So every single point in the closed ball is in fact a point in the closure of the open ball. And similarly, any point, none of these boundary points, none of them are interior points. So the boundary of the open, so the interior of the closed ball is indeed the open ball. So, but that's special to Euclidean space. There are metric spaces where the interior of the closed ball is bigger than the open ball. The closure of the open ball is smaller than the closed ball. So here is an example. Let's let X be. We'll take the origin and we'll union with it the set of all points, a distance of, let's say, 5 from the origin. So the way we're thinking of this is that this figure I've just drawn is basically, we're going to think of that as being the entire universe. Your metric space is this circle and the point in the middle. And then, of course, we think about the ball centered at the middle point of radius r here. And then I'm going to start calling the origin just plain old 0. It makes my life easier. The closed ball centered at 0 of radius 5 is everything. And the entire metric space is an open set, so the interior of the closed ball is also everything. And the open ball is just the origin. And so then the closure of just the origin, I mean, we could draw this ball of radius 1 or 2 or any other number less than 5 around the origin and exclude the outer circle. So the closure of the ball centered at 0 of radius 5 is also just the origin. So we can come up with cases where the interior is smaller than the interior of the closed ball is bigger than the open ball. The closure of the open ball is smaller than the closed ball. And you'll look at much more strange things you can do with the closure and interior and boundary and so on of the balls on your homework. I'd like to give you one more strange example of closures and boundaries. So let's let x be the real numbers. I'm not going to write it down. The metric is the usual absolute values of the distances, and we're going to let a be the rational numbers. Then by theorem way back in chapter 1, 1.2.28, you have to do a little bit more work to get from theorem 1.2.28. It isn't stated quite as I want it, but it'll work. If x is a real number and r is a positive radius, then the ball centered at x of radius r, which in the real numbers we remember is this interval from x minus r up to x plus r, contains a point in Q, a rational, and a point in r minus q. So the boundary of the rational numbers is all the real numbers. Every real number, you draw any ball around it, there's a rational and an irrational. So that means the boundary of the rationals has to be the reals. So the only way that can happen is if the closure of the rationals is all the real numbers and the interior of the rationals is the empty set. And the term for a set that has this property, the term for a set whose closure is all of your metric space, is dense. And then if the closure of A is the entire metric space, we say A is dense. In X. And notice that by proposition 5.3.7b, A is dense if for all points X in your metric space and all positive radii we have that the ball centered at X of radius R contains a point of A. There is at least one point of A in that ball. Intersect the ball with A, you don't get the empty set. And one other thing I'm going to point out in our example, the real numbers we saw in section 1.5 are uncountable. There is, in a very real sense, more real numbers than rationals, but the rationals are countable and they're dense, and we're going to use that, and that fact comes up all the time in analysis. So a metric space like the real numbers, a metric space that's maybe not countable but has a dense subset that is countable, we call that separable. So if X has a countable dense subset, then we say that X is separable. We just saw that the rationals are dense in the reals. I'm going to leave as a possible exercise on the exam that Q to the P, that's the set of all points Q1, Q2, up through QP, where all the coordinates are in are rational numbers, is dense in RP. And also to prove or find in the book where they prove that QP is in fact countable. So not only are the real numbers separable, so is RP. And here's sort of a counterexample to density. Let X be a metric space. Rather, let X be a set, and D the discrete metric, which I'm not going to write out by now. You should remember how the discrete metric works. And then, if A is a subset of X, then A is equal to the interior of A is also equal to the closure of A. And the proof is fairly straightforward. If X is an element of our set, then under the discrete metric, the ball centered at X of radius 1/2. That's the set of all points whose distance to X is less than 1/2. Well, the point X is in that set. The distance from X to X is 0, but every other point in X, the distance to X is 1. The distance is bigger than 1/2. So the ball centered at X of radius 1/2 is just the singleton set containing X. And that means that if X is in A, then the ball centered at X of radius 1/2, that's the same as the set containing X is contained in the set A. So X is in the interior of A. And we know that the reverse implication is true. The interior of A is always contained in A. Conversely, A is contained in the closure. If X is in the closure of A, then the set containing X, that's a superset of the balls that must contain the ball centered at X of radius 1/2 intersect A, because the ball centered at X of radius 1/2 is just the set containing X, but because X is in the closure, this ball is not allowed to be the empty set. So we must have that X, so we must have that the set containing X, that must be a subset of A because it's A intersect this ball. So X must be a point in A. Also, the boundary of A is the closure of A minus interior of A. But since those are the same sets, that's always going to be the empty set. So in the discrete metric, you never have boundaries. So getting back to density, so if A is dense, then X is the closure of A, that's what it means to be dense. And then the closure of A is A because that's how the discrete metric works. So the only dense subset of X is X. Any metric space, the whole space counts as and any point in the metric space is close to some point in the metric space, namely itself, but things like the real numbers and the rational numbers you can find smaller. In the case of the countable rationals and the uncountable reals, much smaller dense sets, but you can't do that with the discrete metric. So the discrete metric on any uncountable set, the discrete metric on the real numbers, say, that would be an example of a non-separable metric space. For the remainder of this video, I would like to remind you of 3 concepts that we talked about in the real numbers last semester that generalize in a very straightforward fashion to the general metric spaces. So I'm not going to write out the proofs in detail because most of you worked them out last semester. I'm just going to remind you of the definitions and the basic facts. So this is, the original version is exercise 1.6.11. The metric space version is definition 5.3.13. So we're going to start with a metric space, a subset of the metric space, and a point X in the metric space. And then we say X is a limit point of A if for all real numbers or rather for all positive radii, there exists a y in A with, you can write it this way, the distance from X to Y has to be both positive and less than R. So between 0 and R, that 0 less than the distance just means Y is not allowed to be the same point as X, or Y is in the ball centered at X of radius R, that's the distance less than R, but it's not the center point X. That's the greater than 0 piece. And then by the same exercise, or in the metric space case, by proposition 5.3.15a, or exercise 1.6.11, or I actually changed this a little bit for last semester. We've got that x is a limit point if and only if there is a sequence of points in our set A that are not the target point, that are not the thing we're saying is the limit point, that converge to our target point X. So this is saying limit points are all the points, all the limits of sequences in A, except for unless the only way you can get to it is just by repeating the point A over and over and over. And then same problem I assigned last semester, and it's actually a proper proposition in chapter 5. Closure of A is always A union with all the limit points. And I think I will not drag you through the proof of this proposition. I will just ask you to go back and look at your proof of problem 21 from last semester. If you weren't with us last semester, you're welcome to ask me about this in office hours if it's confusing. But the idea is that limit points include all the points here on the boundary, whether they're in A or not, all the interior points. But if your set A has some isolated points floating out, an isolated point is a point that's in a set but not a limit point, then those are not limit points. One more definition. I think I will combine definitions 5.3.16 and 5.3.20 in your book. So now we say that if we've got a metric space, a subset of the metric space, and a point in the metric space, we say that the distance from the point X to the set A, we're going to define that as an infimum. It's the infimum of the set of all distances from X to little a, where little a is a point in our subset A of the metric space. And then the diameter is only cares about A, not X. It's similar. It's defined as a supremum of distances. It's the supremum of all the distances from A to B such that A and B are both in A. And we say that if the diameter of A is finite, this is one of those supremums where if there's no finite upper bound, we say the supremum is infinity instead of saying it doesn't exist. Then we say that A is bounded. Here is a quick picture. Here is our set A. Here is our point X. And then the distance from A to X is you draw the shortest straight line you can from X to A. If A happens to be an open set, you might need to take an infimum. And then the diameter is you find the 2 points in A that are the farthest away, and you draw the straight line between them, and that gives you the diameter. Now, you may recall from section 1.6 last semester that the definition back in chapter 1 of the closure of E then the closure of E, it's not defined in terms of the intersection of the closed sets containing E. It's not defined in terms of balls. It's defined as the set of all real numbers, such that the distance and proposition 5.3.17 says that this is equivalent to the definition of closure that we've already seen. And the proof of this is pretty straightforward using some results we've already established. Let's recall that the distance from X to E, it is the greatest lower bound of the distances from X to Y, where Y is in E. And you can always write a greatest lower bound as the supremum of the actual lower bounds. But if there are no points Y and E whose distance to R is 0, this is the supremum of all the real numbers, where the ball centered at X of radius R does not contain any points of E, because that ball is just the set of all points whose distance to X is less than R. So the distance from X to E that is equal to 0 if and only if the ball centered at X of radius R intersect E is not empty for all positive R. That means there's no positive numbers in this set we're taking the supremum of, which is true if and only if X is in the closure of E, and that is by proposition 5.3.7b. I'd like to wrap up chapter 3, so I am going to state the following proposition. The proof is pretty straightforward, so I think I will not drag us through that. So you start with a metric space. And then first part of the proposition is that if X is a point in your metric space and A is a subset of your metric space, then A is bounded, meaning it has a finite diameter, if and only if there is a positive radius R such that A is contained in the ball centered at X of radius R. And this follows pretty much from the triangle inequality. You draw your point X. I guess we've got a point X over here. You just take the distance from X to A, and then you add the diameter, and every point in A must be inside that ball. Second part of this proposition is that if A1 and A2 are bounded, so is A1 union A2. And by induction, this is true for any union of finitely many bounded sets. And part C is that all Cauchy sequences are bounded. And the proof of this is not terribly complicated, so I'll leave you to think that over for yourself.